Ok, alle klare? Velkommen. Jeg føler jeg går inn i vepsebolet her, som sånn Rust-fan, som kommer på C++-konferanse. Yes, sorry, I'm doing it in English. I started in the wrong language. I feel like I'm entering the wasp's nest when I'm coming to C++ conference and advocating Rust, so please don't eat me. This is me, as you see. I'm an embed developer at Inventas, and I'm a self-acclaimed Rust evangelist. So I sometimes go around and talk about Rust and point at screens. I also climb. Let's get started on today's task. I'm gonna show you how to do a very simple embedded project on the nRF52 using the radio to make an LED on a different device blink. Simple setup, 2 or more devices. Each device has a button and an LED. And if you push the button, the other one blinks. We're using the nRF52 from Nordic. Nice little chip with built-in 2.4 gigahertz. Cortex MPU, nor MCU. Yeah, we're gonna use the IEEE, long number sequence protocol. Yes, it's not supported on all nRF52s, so just heads up if you're trying to do this yourself. I tried to use the nRF thingy, and it doesn't support it, so I had to make my own hardware. Just very quickly about the protocol. It's the kind of a low-level protocol that is used by Zigbee and Thread. So it's found in all the smart light bulbs and stuff in your home. So if you look at this diagram here, we're just doing the lower thing. We're on the red arrow. We're just directly to the low level. So it's fairly simple. You can just send a payload to one of 16 channels and just hope that someone will receive it. Yeah, so these are the actual chips that supports the protocol. We're doing it in Rust, of course. It's a memory-safe language. I don't know if any of you heard the talk from just at room 1 now about memory safety. Yes, good. Rich type system, generics, all the modern stuff. Strive towards zero-cost abstractions. So the abstractions should be as good as if you did it kind of by hand. The aim is not to have an overhead. So that's why Rust is a good fit for a small microcontroller. It's not a cult. I mean, you might have heard that we're religious fanatics, and I promise you, we're not a cult. Yeah, sorry about that. We're not a cult. So I'm just gonna ask you guys, how many here have like touched Rust, like done a hello world? Okay, quite a few. How many have people have actually written like something, an application? Okay, a few. And how many uses it at work? Okay, a few hands. Good. So I'm not gonna teach you Rust today. That's a big topic. So, God didn't like that. Yeah. Am I still amplified? Okay, good. Okay, so I'm not teaching Rust today, so I'm just going to assume that you can kind of follow along. But please just like ask questions if something is unclear. Yeah. Yeah, Rust, you can use it from everything from like front-end web to down to embedded stuff. It covers the whole, the full stack. Okay, I made this little diagram just to show the application. It's pretty simple. We listen for events. There's 2 events. You can have a button push, then we send LED on command. Wait for 1 second, just so that the blink is long enough that you can see it. Wait for button release, send LED off. If we receive the LED on command, we turn it on, wait for the off command, and turn it off. Should be easy enough. So let's dive into it. I made this little button abstraction. Here you see some beautiful Rust code. We're using the GPIO-TE from Nordic to handle events on the pins, just like interrupts almost. So we set up this channel 0 and with the input pin that we get, and use this toggle. That means that any activity on pin, we want that to generate an event. Okay, so we have to debounce the button. I originally used hardware with a hardware debouncer, and I switched, and then I had to implement this. So the code is more involved than I was hoping for. But anyway, we want to kind of get the events from the button. So we have this function that I've called debounce event. It returns an option here. That's a Rust enum type. So it might return none. So if there is an event, we have to kind of open the to see if there's we had to either none or some event on the option type. We check if the event is triggered. If it is, we do the debouncing. I'm not gonna go into detail. We just look for a stable value over 10 milliseconds. Reset the event, and then we check the value, and either it's released or pushed has happened, and we return wrap it in sum, and if it's not been triggered, it's not. Does this make sense? Like the option and like the concept of enum types and in Rust? Okay, good. Super easy LED container. This one takes a generic type, P. So it can be any value, but here we constrain it to implement the output pin trait. So Rust, the embedded Rust ecosystem has this like common traits that we can use. So we have common traits for pins, GPIOs, and serial buses, and everything. So we're using that here. That means we can write this LED struct, and we can use it for any microcontroller. We can mock the pins for testing, so it's easy to reuse. This is the trait as defined in the embedded HAL library. You can set low and you can set high. We use them here. Yes. Nordic has no official support for Rust, which is a shame, I think. So, anyone from Nordic here today? One guy? Okay, so I was gonna have this emotional appeal to the Nordic employees and tell them to like go back to your boss and tell them to use Rust, because as we just saw at room 1 with Helge Penne, we shouldn't start a new project in C++, but maybe not C. maybe we should just, at least the vendors should support Rust and show that they also believe in memory safety on embedded devices. So you can join the strike force. You know, just call me, call HQ, and we'll get you set up to go and fight the good fight. But anyway, we don't need Nordic, you know, because we have this great community, and they have made this NRF HAL to support the NRF chip, and that's what we're using today. Yes. So we're just gonna dive right into it. We're gonna initialize the radio on the chip, and I'm also gonna show you how the Rust type system helps us to do things to avoid having runtime errors. First, we have to configure the external clock. You can't use the radio with the default internal clock, so we set this up here. This is a function from the community supported library. It gives us this like clock struct, and it has some generic parameters. So if you see this external oscillator, it becomes kind of part of the type, the fact that we have configured it to use the external one. And that's going to be used by this function. So to initialize the radio, we need to provide this struct with the external oscillator. And since there's only one way to construct this value is through the enable external oscillator function, when we have this valid struct with this type, we know that the radio is the clock is correctly set up for the radio to work. So, which is a really nice feature, and this is called a type state pattern, and it's widely used in Rust to ensure, especially on embedded Rust, to ensure that we can't really express incompatible setups. We can't use the radio with the internal clock. Yeah. And then we want to receive data from the radio. And the library comes with this nice little receive function that can receive data into a buffer, but it's blocking, and that doesn't really work for our use case here, because we're going to listen for the button press and listen for data at the same time. So we need something, and we're doing this in a superloop because keeping it simple. So it's not really, it doesn't work with our use case. So I did myself and made a pull request. So I have implemented this non-blocking receive and submitted to the NRF HAL GitHub. And as you can see here, the internet is not broken. There's random people helping each other out and doing good stuff together. So we can just relax and have believe in the future. This is my new function to do the non-blocking receive. It is a bit more complex, and I guess some of the reasons for that is that because Rust provides memory safety, it also means that there's kind of a higher bar for things to be considered safe Rust. We're dealing with very unsafe stuff now because we're dealing with the hardware and DMA operations. So I had to make this a bit more complicated because we're passing this mutable reference to the data. And and since we're doing this non-blocking, we can't if we risk this buffer being freed before the transfer is done, all of a sudden you have a kind of used after free, but from the hardware. So to prevent this, the function actually takes a function as an argument here. So the actual handling of the kind of the non-blocking code happens inside this closure that's provided to the function to make sure that the packet lifetime is guaranteed to outlive the transfer, the receive call. I'm getting into more detail. So this function takes this is a closure that takes this receive object. This is just a struct to kind of handle be a handle for the receive operation. It has one function to check if the transfer is done. It's either yeah, to check if it's done. It uses this non-blocking library that provides kind of a special error type. So there's kind of three options there. Either it's okay, which means that the transfer is correct. In this case, you receive data and the CRC check was good. Or you receive data and you have an invalid CRC. Then you get this other. But if in case that you haven't received the data yet, you get this would block. So instead of blocking, it just says this would block if it was a blocking call. So we can call this is done over and over until we get something other than would block. So here's how we use this function. So we have provided here a closure, a Rust closure, which is an anonymous function that can also capture stuff from its environment. But in this case, we're not capturing anything. But it takes this receive argument, then we get this receive handle. And you do a match. But first, we have a loop here. So this loops, and it repeatedly calls is done. And if you get like an okay or the other, then we break out the loop. Or else we just continue looping if we get the would block. So this is now we just basically created a blocking function from the non-blocking. But I'll show you next how we use it in our application. Any questions so far? Then I'll just continue here. Yeah. Yeah, I had this highlighting and I forgot about it. Okay. Yeah. Yes. This is our superloop. There's a lot of code here I'm not showing you because it's just setting up the embedded stuff. I have a full example that you can check out later, but this is just to show the essence of the code. So first, we get an event. And this is our event. This is our code to get the event. So there's two events. This is all done inside this non-blocking closure. So inside here we have started the transfer, and it might or might not be done. We start with checking the button. Did someone push the button? Did we get this button push event? If so, yes, we break out. So define these events here. And then if that didn't happen, we check, did we receive? Is the receive done? If so, yes, great, packet received, or invalid packet. We also break because the receive is finished. Woodblock, we continue. The continue here is we could drop it because there's nothing below here, but I just add it for clarity. So we're kind of and we're binding here the I'm just gonna go back. I forgot to mention one thing, important thing here. Let's see. Yes. So the return type of the closure is generic. And also the receive also returns this generic type. So whatever the return value of the closure is, that's what we get back. So any value is okay there. Yeah, so this whole thing here returns when we break with an argument, the kind of loop returns this value, and that's what the whole function call returns, and that's what we store inside the event variable. Okay, so we have the event. Now we can handle each of the 3 cases. If we get the CRC error, we just continue looping, so that's not really interesting. But the button pushed and packet received, that's where the magic happens. Button is pushed. We have defined like 2 simple commands. It's just a byte string that we can send over the radio. So we send the data, and then we just chill out for a second, and then we go back and check if the button has been released since then. It's just to have minimum time for the blink, and then we send the off command. So pretty simple. And even simpler, on the receive side, we receive the packet. We check did we get the right packet that we're looking for? If so, turn on. Wait for the off command, and then turn off. Okay. It's demo time. I brought actual hardware. I had this idea that I would build this like slick prototype and print the case and everything, but this this is what I ended up with. And please, just before anyone says anything, this is not a bomb. It's just I'm a lowly software developer trying to do hardware. So that's what I end up with. I have 2 of these here. I'm just gonna, there's no off button, so I just remove the batteries. Is it possible to like turn off the lights, or is this some kind of automatic system here? Because these LEDs are, yeah, a bit dim. Okay, so any volunteers? I promise you, it's not gonna explode. Okay. Yes, okay, so I guess you go first, press the button, and you hold it up. Yay! And then the other way around. Thank you. The simple joys of embedded development. You know, it's the best part of the project is when you get that LED to blink. What? Yes. It's like magic. Yeah. So why why should you care about embedded Rust? I have some points here, and I was hoping maybe to see if you have any thoughts on that.
Compile time pin safety. Compile time pin safety.
Compile time pin safety.
Yes.
Yes, for the.
For like I2C data, I2C clock traits. You can't misconfigure a device as long as the BSP is right.
That's correct. Yeah, you can encode. You can use the rich type system to encode information about yeah.
Can't mix up UART pairs.
Yeah. Memory safety means fewer bugs. And I think what it actually means is that with fewer. Yes, bra. With fewer bugs, that means you spend less time debugging, which is not fun, and you spend more time writing software, which is fun. So it more fun should actually be the headline here. Rust comes with cargo, so you have a package manager. You want to use the latest cool RTOS, you just cargo add, and whoops, it's in the build system and it just works. No more like fiddling with the CMake stuff. Yeah, I still don't understand CMake. It makes no sense to me. I tried many times to learn CMake, and it's just it's impossible. High-level features from lots of the inspiration in Rust is from functional programming. So if you've done like Python and Haskell and stuff, you can use lots of those patterns in Rust on an embedded system, which is really cool. And async you can also do on embedded. So instead of having like in free RTOs, you have a stack for each task, and you start to struggle with memory. If you're doing async tasks, each task only uses the amount of memory it needs, and it's all figured out at compile time. Type state moves errors from runtime to compile time. So that's the real strength. So you can, for example, if you are working with GPIOs, you can encode it in type system that this is configured as an output pin, or an input pin. And if it's configured as an input pin, you just can't change the value of it. And so no more like undefined, no more weird errors where you thought you had it configured correctly and you didn't. Or in case of you using some pins as for I2C, the alternate function is already encoded in the type, so you know that your pins are set up correctly when you configure the bus. The embedded HAL, it's common traits for embedded systems, community supported, so you can make high-level libraries for example, let's say you have 7-segment display driver that you made. You can make it generic for all kind of systems. And you can also swap out, let's say you want to use an IO expander instead of driving the pins directly. Super easy to use if you use these traits. Great tools. Cargo is the kind of the Swiss Army knife of Rust. You can build and you can add extensions to it to run code directly on MCU. And there's a friendly community. Not a cult. Yeah, definitely not. I'm just gonna show one more thing here, because at the C++ Where Do We Go Now talk that was just happened, there was a nice slide. I took a picture of it. I think we need to zoom in here. Where's the So the topic here, for those who didn't go, is like C++ is not memory safe. How do we fix it? And here's basically the suggestion. The solution is to make C++ like Rust. I'm thinking like, why can't you just use Rust if we have to change all of C++ to make it memory safe? Let's see. Yeah. Okay. So, any thoughts on why we should use Rust or not? Yeah.
Did you do some comparison on the size of the image you get?
Not for this, but
You see the benefits in terms of size?
in terms of code size,
Yeah, memory
I haven't done like any comparison, but I don't see why it would be any different from C. With a similar footprint, I guess. Yeah. Yeah, and if you do link time optimizations, you kind of peel away like
You can slice
all the unused stuff. Yeah.
Another question for me. Did you ever try to use Zephyr?
Yes, I've tried to use Zephyr for the Nordic. I haven't used a lot, but like I really don't like Zephyr. Like the macro abuse in Zephyr is just it's too much. So, but now I heard they got Rust support in Zephyr, so maybe I'll give it another chance. They're working on it.
Yes.
Okay.
Which is super cool.
That's super cool because then maybe Zephyr is usable, and and especially if you can use cargo and don't have to use CMake and West, that'd be great. Yeah.
Sorry,
Yeah.
which compiler do you use? Who are the compiler vendors for embedded Rust?
So for this project, I just use plain old the default Rust compiler and the default linker. But
Cross compiler.
so Rust uses LLVM under the hood, so you get that for free. So you just had to add like the target, yeah. But in a different project I'm working on now, I have to link in like some vendor libraries that's written in C, and the default Rust linker didn't really play nice with that. So then I'm using GCC as the linker, and that works. So you can swap out the linker easily in cargo.
If you require like a certified compiler, there is FairC.
Yeah. Yeah, it looks pretty promising. Yeah.
How does Rust deal with interrupts? Because I guess that becomes a problem with your memory.
Interrupts are challenging because you need some kind of global mutable state. So there are many different ways of dealing with that, but kind of the key is you have to kind of encapsulate the global state in something a bit safer. So on a single core microcontroller, you would probably use critical sections to ensure that you don't have a data race with interrupts. If you have multi-core, then yeah, it's more complex. Probably atomics would be the solution. If you have the RP2040 with no atomics and 2 cores, yeah, then you're out of luck. Yeah.
Just wondering, when you're reading a package, did you also like the loop construct? Did you actually loop over to read, or would you get an actual input from?
This I just did the superloop implementation here.
Yeah.
You could get an interrupt.
Okay.
I'm not sure if that. So the library I'm using did only support the blocking use case. So I added a non-blocking, and it would be possible to add an interrupt driven use case as well. But it's community supported, so you only have what people needed before.
This was the product that is an absolute requirements, and in between that, you need to go into the low power state. So
Yeah, then I would go. It's just like Rust code, so you can just go and contribute the changes to the library and get it working. That's my suggestion. Yeah.
How active is the nRF52 library? Is there similar than other vendor libraries?
Yeah. There's for each like common microcontroller, you'll find a community supported packet and library. And I submitted this PR, and they responded immediately. And they were very friendly, and they had some concerns with my initial proposal, and I fixed those, and it's all good. It hasn't been merged yet because they're waiting for some more reviews, but yeah. And that's my general experience. That it's super easy to contribute to these projects, and they are like very interested in having, especially if you actually submit code pull requests instead of just like complaining on an issue. They are super friendly. Okay, anyone else? Yeah.
What's the biggest pain in the process?
So the biggest pain, I would say lack of vendor support is a pain point, because you don't cover all use cases, and it also kind of sends a signal that it's not being taken seriously. I mean, if you want memory safety, there will be pain points. I think that's it's very hard to avoid, because lots of the pain points in Rust are dealing with lifetimes and the borrow checker. And I'm not sure if there's a way around that. I mean, in a way, you're already dealing with these issues in any code base, but in Rust, it's very explicit and enforced by the compiler. That makes it a bit harder. But okay, so kind of the biggest challenge is maybe when writing embedded Rust, you have to write unsafe code at some point to interact with the hardware, and the interaction between safe and unsafe is challenging, because the stuff you do in unsafe can infect the safe code if you don't uphold all the guarantees of the Rust compiler. So if you write unsafe code that writes data into a non-mutable reference, that's instant undefined behavior, and it could blow up your application. Maybe not when the write happens, but at some later point. And you have to manage that, because the Rust compiler assumes that safe code is safe and upholds all the guarantees, and will optimize your code based on that. So in C, you kind of, it's a free for all, but in Rust you have to be more disciplined. Yeah.
What's the state of real-time operating systems?
So there are a few kind of Rust native alternatives. There's one called Arctic that's has kind of a novel approach to uses the interrupt controller as a scheduler, which is kind of yeah. I mean, you can use any. I use free RTOs from Rust, which works fine. But I think the most promising is the async. There's a project called Embassy that has this async runtime for Rust. So you get very like small memory footprint tasks, and it's. I mean, since you're single threaded anyway, it doesn't really. Yeah. So it's easier to kind of reason about the cooperative multitasking in a way on a small system. At least I find that. Yeah, okay. I put out the code for the demo. If anyone wants to have a closer look, it's all tied to my hardware, so you have to update the pin numbering, but it should work. You want to buy this? Maybe I'll make a kit with the glue gun and everything included. Yeah.
Do you have any experience with converting C code to
To like take an existing code base.
Of course, you can directly but are there tools that can
There's a tool.
take
Yeah.
basic, part of your application that you can modify basically, that you don't have to write it from scratch?
Yeah, I haven't tried those tools. I've heard about the C to Rust tool. What I probably would do was, and what I have done is to instead of rewriting everything in Rust, to kind of just include have Rust and C live side by side, and then slowly migrate the code to Rust. The stuff you would rewrite anyway, probably. That would be my approach. I don't think it's worth it to do the C to Rust conversion. You would get really nasty Rust code, I guess. And it would be all the code you kind of export from C to Rust would all be unsafe, so you get no benefits. Yeah.
Their goal is translating all C.
Yeah, there's a lot of projects trying to rewrite all the GNU core utils in Rust, and when you do a full rewrite, I wouldn't do the translation. It's the chance to structure the code and get rid of like 30 years of legacy.
So with the Rust interface, you can call
Yeah. It's easy to call C from Rust and vice versa, because Rust can kind of expose C ABI for structs and functions, and yeah. So I have a project now dealing with we're interfacing with Xilinx libraries and also free RTOs in a Rust application, and it's yeah, works well.
Another question, you mentioned nRF, how
Yeah.
Are there any different same or the different?
So the embedded HAL is the generic HAL that's kind of the foundation of the embedded community. So there's no functionality there to work with an actual microcontroller. It's just a set of common traits to do common operations, like the output pin trait. So the nRF it kind of depends on the embedded HAL. Yeah, and so would all the crates, the STM32 and RP2040 HALs also use embedded HAL. Yeah.
Just a comment on that. If the community works hard on that, maybe, hopefully, you can have the different manufacturers all working with that system instead of everyone having their own libraries, so that your code base has to have a layer in between the manufacturer code.
That would be the dream, yeah. And that's the hope of the embedded working group. So hopefully, yeah, like I think if like Nordic was to support Rust, I would prefer it to be done in a kind of community-based way, so that you that Nordic would contribute to the open source community library, and that we as users of that can also fix errors and contribute our solutions. Because the way the embedded vendors are set up now is that they write the library once and then ship it in some tarball, and then maybe you can file a bug complaint that gets like dropped in a bucket somewhere and never fixed, which is pretty frustrating. But this model might be definitely could be a model for how we do vendor support and kind of cross microcontroller support.
Another model we work with Zephyr, like most of the kernel code and everything, the common parts is upstreamed.
Yeah.
And we add our own things which might be licensed or can't be shared, or it's just Node specific. So that would be exactly that model.
Yeah, that's good.
I just wanted to talk about Arctos. I mean, Zephyr is in Arctos, but it's also, it has file system reputation, it has a driver infrastructure, it has an IP stack, which is a huge work. So there's quite a lot of things that need to be in place.
Yeah.
We have all that in C, and it's kind of proven. So it's and C is not going away. That will stay there.
Yeah.
It's coming in addition, and we need to be just as good. That's kind of the barrier.
Yeah, I think with Rust support coming into Zephyr, that's probably the way to go. So we can kind of have the best of both worlds.
Application, at least in Rust, and you can benefit from
the
rest of the sort of middleware that is available.
Yeah, and then you can also start, if you can implement new drivers in Zephyr in Rust, so you have Rust at both ends. Would be great. I don't know how the Rust support in Zephyr is set up now, but
I think it's in the works. It's going to be layer on top.
Yeah, layer on top first.
It will be, Linux is basically mainly C, but then you can
Have the kernel modules in Rust. Yeah. Yes, I think, how are we on time? I guess, yeah, 10 minutes early. Yeah, that's all for me. Thank you.